this is recording. RTI
International
Center for
Forensic
Science
presents
Just Science.
Welcome to Just Science, a podcast for justice professionals and anyone interested in learning more about forensic science, innovative technology, current research, and actionable strategies to improve the criminal justice system. Just Science interviews Dr. Tatiana Trejos, Assistant Professor of the Department of Forensic and Investigative Sciences at West Virginia University, about the rapid detection of organic and inorganic gunshot residue. Speed and accuracy are vital when it comes to the analysis of gunshot residue. Dr. Trejos and her team are working on a comprehensive method for studying both organic and inorganic gunshot residue utilizing laser-induced breakdown spectroscopy. This method focuses on providing accurate results, reducing wait time, and preserving the evidence. Listen along as she discusses chemometrics and a novel tool for analyzing organic and inorganic gunshot residue in this episode of Just Science. This season is funded by the National Institute of Justice's Forensic Technology Center of Excellence. Here is your host, Dr. Megan Grabenauer.
Hello and welcome to Just Science. I'm your host, Dr. Megan Grabenauer, with the Forensic Technology Center of Excellence, which is a program of the National Institute of Justice. Today our guest is Dr. Tatiana Trejos, an assistant professor of the Department of Forensic and Investigative Sciences at West Virginia University. Tatiana, welcome to the podcast.
Thank you, Megan.
So looking at your bio, it says that you teach research design courses. I don't recall ever being offered anything along the lines of research design when I was in grad school. It was much more trial and error process. So what kind of topics do you cover in a course like that?
So as you may know, West Virginia University is one of the only two universities in the United States that offer a PhD program in forensic science. And so the program was developed to respond to the need for more specialized workforce. And one of the main objectives of the program is to prepare a new generation of forensic scientists that have better tools to provide solutions to forensic problems. So we want to prepare well-rounded individuals who have more in-depth knowledge in statistics. So we try to incorporate a little bit more of that in our curriculum for our grad students. So the program usually offers at least 3 classes in statistics, and the research design course that I teach was custom-made for our doctoral students. So the course is an applied research and statistics-based course that introduces students to the analysis of simple and complex problems, of forensic data, and how they can design experiments and interpret the results to make those experiments more cost-effective.
So you go over things like appropriate sample size and sampling and
That's
inclusion
correct.
criteria, things like
That's
that?
correct. So the first portion of the class teaches students several models of conducting cost-effective research designs. So starting by identifying early when they are building the hypothesis. What are the relevant questions to answer? What are the variables and factors that can affect the outcomes of the research? What is, as you said, the proper sampling size, which is the $1 million question that we have every time that we start doing a research. How many samples is enough, right? And the answer usually is that we always need more.
More than you can afford to do,
Exactly.
either for time or resources.
So that's one of the things that we all go over with the students. So this is your problem, and this is the variables, this is the question that you want to answer. How many samples do we need to get appropriate power of the test without having to waste resources and things like that? So you will be surprised how much time and effort and cost can be saved with proper experimental design. So we try to teach that to the students with real case examples. How is it different if you have to set up this same experiment for a research setting versus a case-work setting? And most importantly, how you can do it with a mindset that if you are doing a research, it will eventually be applicable to the crime scene or to the crime laboratory. So that's something that we try to teach in the research design, how we can prevent to make sure the models that we're using fit for purpose, that they are statistically valid, that we are using and trying to think in advance all the possible factors that can affect my outcomes.
So I know that a lot of your research up to this point has involved something that we call chemometrics, which is a term that a lot of people may not be too familiar with. Would you mind going into a little bit of detail to explain what chemometrics is?
Yeah, absolutely. So chemometric is the use of mathematical and statistical methods to improve the understanding of chemical information, and that's what the chemo comes from, or information forensic data, for example. So I would say it's a fancy way of saying that we are applying statistics, but we are aware that I'm not a statistician. So it's application of math and stats to solve chemical problems, work with chemical data, forensic data.
So do you need a strong background then in math and statistics to go into this field?
Well, not really. I'm not a statistician, and I didn't have a lot of statistics classes in my career, so it was more like a self-learning process. Also, collaboration over the years as a practitioner and also in the academia with real statisticians have helped a lot in that process. So just to give you an example, the class that we were discussing earlier, that is heavy in statistics, right? We cover many other aspects, like, for example, interpretation of evidence, including Bayesian methods, and that's not an area that I completely am expert of. So what I normally do in those classes is that I invite guest speakers that are statisticians, and they graciously come and talk to the students, present their expertise in forensic science. So for example, last year in the class, I had the opportunity to have as a guest speaker James Curran from the University of Auckland, who is like an expert in statistics and forensic science as well, application of statistics to forensic problems, including DNA and trace evidence. So I took the challenge to teach this type of classes and incorporate statistics in my research, but I'm not a statistician. And that's something that we really want to change with our programs.
That really sets a good role model, though, for you. You're not an expert in the field of statistics. You recognize that, so you bring in the expert to teach the students. I think it really helps to kind of impress upon them. You don't have to do it all. You can collaborate and bring in people with different expertise when it's necessary.
Yes, one of my mentors always told me one of the big lessons is that you don't need to know everything. You need to know who to collaborate with.
And that's actually how I met you in the first place, as we were starting to get into gunshot residue research area, and I contacted Dr. Suzanne Bell. And she said, well, you really should get in touch with this new up-and-coming professor that West Virginia University hired, and you guys could collaborate on some proposals and things together.
That's right.
But going back to the statistics question, I've noticed, too, that it's becoming more important in the area of forensics, and some of the more recent NIJ research and development solicitations that have come out, which are what you have to respond to if you want to get a research grant. There's a new requirement in there that you have to have a power analysis for your sample size.
That's absolutely true. And that's one of the things, the very first thing that I teach now in this research design class. How do you calculate and estimate a power of analysis? How many different tools you can use to estimate it from experimental data or from literature as well? And how do you apply depending on what is the hypothesis that you're formulating, what are the answers that you want to be looking at, what are the factors, what are the tests that you're going to be applying to test your hypothesis. So that's something that I actually enjoy teaching to the students, because it's something that we didn't have to do 5 years ago when we were writing grants. Now we have to prove that the experimental design that we are proposing is going to have enough statistical power. So that brings an example how we have to evolve, and we have to use statistics more and more often to prove the reliability of our methods, the validation of our methods, the power of what we are proposing, so that we can really bring generalized conclusions rather than a conclusion that only applies to a particular study.
This week we are at the American Academy of Forensic Sciences annual meeting in Anaheim, California, and you presented at part of the NIJ Forensic R&D Symposium earlier in the week, a presentation entitled Rapid Detection of Inorganic and Organic Firearm Discharge Residues by Laser-Induced Breakdown Spectroscopy and Electrochemical Sensors. So Tatiana, before we get into the details of your project, are there any other researchers who contributed that you'd like to acknowledge?
Thanks for asking that question. I'm very glad that you asked that. This is a very ambitious study, and we could not have done it with many contributions and collaborators. So my undergrad students, Emily Heller, Zachary Andrews, Emily Halpern, Oriana Ovid, and Courtney Delsel. Also grad students, Corina Menking-Hoggett, Cornet Vanderpyle, Colby Ott, Bill Finney, Pedro Calderon. A postdoc student, Claudia Martinez Lopez. We have collaborators at the university level. So we have James Curran, which is chair of the Department of Statistics in New Zealand. He is our statistician in the project, so he has been a fantastic resource for the interpretation aspect of this project. We also have another in-house statistician that has been very helpful. Her name is Stacy Kolb. Also at WVU, in the Department of Forensic and Investigative Science, we have Dr. Kit Morris, who has been a key collaborator in our project. We have ballistic laboratory in our department. Also my colleague Suzanne Bell, who is recently retired, but she has laid down a lot of the foundation on research on gunshot residues. From WVU, we also have Paul Speaker from the Department of Finance, and he is the one that managed the Foresight project, so that when eventually we want to do plannings for transition of the technology, he is going to be helping us with pilot laboratories to estimate the return of investment and see how much the adoption of this technology can really improve the efficiency at the laboratory and at the crime scene. And we also have collaborators, international collaborators at the University of Costa Rica, Ana Lorena Alvarado. And from the industry, we had Foothold Labs and Applied Spectra from electrochemistry and LIBS respectively that have been very helpful as well to work with us with how we can make this technology portable. And also our contributors from the crime laboratories and practitioners. We have Chip Pollock from the Sacramento Crime Laboratory.
I often hear both the terms firearm discharge residue and gunshot residue. Just let's get that out of the way right off the bat. Are those terms synonymous?
They are used as synonyms. I think that fire discharge residue is used more like a more overarching general term. Gunshot residue has two main components. The inorganic gunshot residues coming usually mostly from the primer, and then the organic gunshot residue coming mostly from the propellant. So we normally refer to those two terms together as firearm discharge residues.
Okay, that makes sense. I never knew that, but now it's all becoming clear. Can you briefly describe how firearm discharge residue or suspected residue has traditionally been analyzed? You're developing newer methods, so let's start with what crime labs have been using up to this point.
Gunshot residue is currently analyzed by standard methods using SEM-EDS. This method has unique advantages that it allows to observe the typical spheroid morphology of a gunshot residue particle. Often these particles are spheroid and are around 1 to 10 micron in diameter. And this instrumentation has the capability to magnify many times to be able to look at that morphology of very small particles. And the instrumentation also has the capability to do elemental composition in addition to the morphology. So with standard ammunitions like heavy metals like lead, barium, and antimony are very relevant markers of GSR. And this method is used as a standard protocol in forensic laboratories. Practitioners are trained already on the operation and instrumentation, so it's pretty much established technique all over the United States and abroad as well to do identification of gunshot residues.
What is driving you to look into newer methods? What are the current challenges or places where the standard methods fall short?
So regardless of its scientific validity, we still face several challenges in the field. One of them is that the current methods, such as SEM-EDS, are very time-consuming. Just to give you an example, it can take up to 8 hours to do the analysis of one sample. In a typical case, will contain at least 4 samples per individual. If we are sampling the hands, we are going to be sampling right and left, back and palm, plus a negative control, just to make sure that there was no cross-contamination. So if you start multiplying 8 hours per sample,
that adds usually very fast. Yeah.
Yes, that adds very fast, and usually can take several days to do one case. So although the technique is great in the sense that, as I mentioned, it can provide morphology, it can provide elemental composition, it's very robust, it's standardized, which is a great plus. The scientific reliability has been established. It is very time consuming, so that's one of the limitations that we have with this methodology. And therefore there is a need to find alternative analytical tools that can provide faster results without sacrificing the quality of the data. Another limitation of SEM-EDS is that it can only analyze the inorganic constituents of the GSR, which are somehow prevalent in the environment. We can find lead, barium, and antimony from many other sources. Soil, mechanics tends to have high levels of these elements in their hands as well. So in order to decrease the potential for false positives, the community is looking at complementing the inorganic analysis with identification of organic constituents like the ones coming from the propellant or the gunpowder, and the stabilizers that are used also in those formulations. But at this moment, there are no standard consensus methods available for the analysis of the organic constituents. So that's where our technology is coming, try to overcome some of those limitations. Can we do this in a faster way? Can we develop a method in which it can take only minutes instead of hours? And can we do detection both of inorganic and organic gunshot residues so that we can provide more confidence in our conclusions?
So in your presentation this week, another thing you mentioned is that the standard ammunition is no longer standard. So what is it about the ammunition that is changing that's different about it?
Okay, so when I refer to standard ammunition, I mean ammunition that contain the components in the primer crop of the cartridge that typically are lead, barium, and antimony. Those three elements are considered markers that are characteristic of inorganic gunshot residue. And normally a standard ammunition will contain those three markers, and that will help us as a forensic examiners if we find morphology and the presence on that particular particle of these three markers. That provides confidence that we are dealing with GSR over something else that looks spherical, but it may not be a GSR. However, due to environmental concerns, lead-free and toxic-free ammunition is becoming more common, and that brings a series of challenges as other elements are used in the formulation instead of lead, barium, and antimony, some of which are even more prevalent in the environment, in the background population, and not as distinctive or what we call unique to gunshot residue formulations. And therefore the need to expand our capabilities to detect other markers like organic gunshot residues. So that's what I refer about. They are not as a standard anymore, because we often now find a standard ammunition that is labeled as a standard and doesn't contain the three elements. We can find standard ammunition that only contains lead and antimony, but not barium at all. Or we can find lead-free ammunition that is sold as lead-free or marketed as lead-free and contains still the heavy metals, including the lead. So the formulations are changing a lot, and with that we need to find a way to adapt, to have better capabilities to detect those changes in the formulation and still have the power of identifying that as a gunshot residue over something else that may have similar composition.
One of the technologies that you're looking into to fill this gap is laser-induced breakdown spectroscopy. I'm personally not too familiar with laser-induced breakdown spectroscopy. Can you go into a little more detail about what exactly that technology is?
Laser-induced breakdown spectroscopy is an analytical technique that can do direct analysis from solid, liquids, and gases, so it's very versatile. So how it works is that we have a laser beam that is very, very fine in diameter. Usually it can be from 4 microns in diameter to 100 microns in diameter. So you can fire that laser of high energy directly into your sample, and that is going to create a temporal microplasma. So that microplasma basically is a hot environment that contains excited species. And those excited species very rapidly are going to go back to the ground level. When they do that, they emit a light that is characteristic of the elements that are present in the sample. So we have spectrographs that have the capability to separate the different wavelengths of the elements that are present and do a detection of many elements simultaneously. So in theory, we can have almost every element present in the periodic table detected by leads in just few seconds. So it's a very versatile technique.
So what is the sensitivity of that? How many molecules of a certain element would need to be present for you to be able to pick it up using LIBS?
So the limits of detection of leaps depends on elements. There are elements that are more sensitive than others, but typically we can detect elements that are present in the low ppm range, so pretty low concentrations. It's fairly sensitive.
Then along with LIBS, you're also looking at electrochemical methods. So what information are the electrochemical methods able to provide?
So the electrochemical methods work under another principle. What they are looking is at the reaction, redox reactions of the species under the stimulation of current or electricity. So what happens is that when we have molecules that are active to electrochemistry, we can detect organic and inorganic components at the same time. So the advantages of this method is a very, very mature technique. It's a technique that has been used for over 60 years in the biomedical, in the environmental industry, in the chemical industry. Just to give you an example, we use it every day, for example, in the detection of glucose. Those that pinch your finger to get some detection of the blood and detect what is your blood sugar level. Some of those are based on electrochemical detection. So the same thing or the same principle applies to gunshot residues. It's a very useful and disposable electrode that it looks like a strip of only about 2 centimeters in length, and that can be incorporated to a portable device that is not bigger than an iPhone. So we can use it to detect in situ the presence of gunshot residues. So the species are going to be active to electrochemical process. And when that happens, we can detect simultaneously in less than 1 or 2 minutes the elements that are present. In this case, for example, the barium antimony plus the organic constituents that are present in the gunshot residue.
Both LIBS and the electrochemical analysis are much faster than the SEM approach.
A lot faster, yes. So the leaps can take seconds. So we normally do 25 replicates per sample instead of just doing one single analysis per sample. And that takes only about 1.5 minutes. And then we can, immediately after doing leaps, we can do the electrochemistry experiment on the same exact sample, and that usually takes less than 3 minutes. So overall, we're talking that doing both leaps and electrochemistry, detecting organic and inorganic gunshot residues can take under 5 minutes per sample. So just to give you an idea of the time savings in comparison to SEM EDS, we still use in our project SEM EDS because that's the gold standard. So when we are developing this in our large populations, we are doing analysis by electrochemistry and leaps. And then on the same sample, we do SEM EDS as our confirmation or cross-validation of what we are obtaining by electrochemistry and leaps. So last summer, we had the opportunity to go and participate doing our research at the World Scout Jamboree in West Virginia. So we were able to collect samples from kids all over the world. So it was a very, very exciting project because that was the first time that we were doing research at a Jamboree Scout event. So we were able to meet kids from all over the world. It was amazing, and we were able to collect samples from their hands right after they were shooting in their barrels.
Oh, okay, that makes more sense than why you thought the scouts might all have gunshot residue on them.
Yes. So we did a collection right after they were doing the shooting sports. And we were able to collect thousands of samples in just 2 days. So it was a fantastic event. We also have another sampling location away from the shooting ranges, in which we also collect background from the hands of individuals that has not fired a gun in the last 24 hours or so. So it was a fantastic opportunity for our group, and we came out with thousands of samples. We were able to analyze about 1,800 samples in 1 week by LIBS and electrochemistry. We are still under 100 samples by SEM EDS. So that has been our challenge because we want to use SEM EDS as our cross-validating method, but we cannot keep up with the speed. So we have to do, it's a lengthy process, and we have to do many less samples than what we can do with the technology that we are applying. And if you think about it, like we were able to analyze these samples in less than a week, which is important, but at the same time, we were able to do the detection very quickly. If we have to spend or wait months before we can finish up processing samples, we also increase the risk of losing the components on the sample as well. So that's another advantage of having faster methods to process the evidence.
Especially for the organic components, right? Some of those may be volatile, so if you have them sitting around for months, they may all volatilize and no longer be on the collection material.
You are correct. So those are the ones that have been shown in different studies that are more prone to be lost over time. So the inorganic aspect of them, like the inorganic gunshot residues, once you collect them and secure them in the carbon adhesive, they can last for several months with no problem. The organic, not so much. So if you don't sample them and analyze them quickly, you have the risk to lose them very, very quickly.
What kind of instrumentation is required to perform this kind of analysis? Do you have to buy a special LIBS system, or is it something that laboratories may already have in-house?
So we have several laboratories in the US that already have LIBS systems in their laboratory. Of course, they are not as spread out like SEM EDS. Every forensic laboratory that do firearm examination or gunshot residue will have an SEM in-house because it's the workhorse instrument in the laboratories. So we cannot say the same thing with LIBS. Not every laboratory will have a LIBS. However, one of the advantages of LIBS is that it's more cost-effective and much easier to maintain. So I will say that the cost of acquisition and maintenance is at least half of what an SEM EDS instrument costs. So in the long term, the return on investment will be very beneficial for the laboratories that want to complement that type of technology. In the other hand, electrochemistry is used universally in many, many areas, aside from forensic science, but it hasn't found its application in forensic science, which is very surprising for me. There's a lot more now research, I will say in the last 3-4 years, using electrochemistry for drug detection and for gunshot residues, but it's not fully incorporated in the forensic laboratories. However, the advantage of electrochemistry is that the technology is available out there. There are dozens of vendors with different instrument configurations for doing electrochemical detection for anything that is portable, like in the size of an iPhone, and something that can be the size of a laptop. And the technology is extremely cheap. You can have electrochemical detection with performance with less than $10,000 per unit. The electrodes that you use are disposable, and they are less than $1 per piece. So the adoption of this technology is something that could be feasible and viable due to the cost of the instrumentation and maintenance. It's very easy to train. Also, personnel is something very easy to pick up and how to operate it, how to understand it. So even though it's not broadly used in the forensic laboratories, I think it has the characteristics and features that will make the adoption of the technology easier in the future.
One of the other advantages I heard you talk about earlier this week is that both types of analyses, both the LIBS and electrochemistry, can be done off of a single sample.
Correct.
Do you have to have any kind of specialized sampling material to make it a minimal LIBS analysis, something different than what you would do for SEM?
Something that we decided at the very, very beginning of our project is that we wanted to use universal collection methods. So we adapted our methods to the current sampling methods instead of the other way around. So we are using the same carbon stops that are used to collect residues from hands that are used by SEM EDS. So there's no need to change any of the protocols that law enforcement agencies have been used for years, so they already know how to use it, how to preserve samples. They're already standardized protocol for crime scene investigators, law enforcement, and for the laboratory personnel. So we didn't want to change that, so we adapted our methods to be able to operate with these type of carbon adhesives.
That's an excellent strategy. So nothing changes then for the frontline personnel who are at the crime scene doing the collection. If this is to be implemented, all those changes are more on the back end of the laboratory analysis side.
Correct, and we didn't want to lose also all the knowledge that exists in terms of stability of these samples once they are collected. We know how they are stable, how you have to storage them. So we didn't want to provide any changes in the front line that will eventually will need also additional studies to demonstrate that they work as well as the techniques that are used nowadays for collection of this type of evidence.
Great. So when you then talked about doing the SEM to verify your libs and electrochemistry analysis, are you also doing SEM on that same sample, all three techniques off the single sample?
Yes, we are using the three techniques on the single sample. So we are using LIBS and electrochemistry as a fast screening tool, but since they are almost non-destructive to the sample, we leave, I will say, more than 80% of that carbon stop unaltered during analysis. So we can do confirmation if we need it by SEM EDS on the same exact sample.
Is there any dependence on the order that you do the analyses? Can you start with SEM and then do LIBS and electrochemistry, or could you start with electrochemistry and then do SEM and then LIBS?
So we have tried different sequences. So we have tried LIBS and electrochemistry, or electrochemistry and LIBS, and we're able to get very similar performances. It really doesn't matter much. We haven't done, however, SEM EDS first for two reasons. First, because what we want to propose is to use this as a front line, the first fast screening that we have to do. If we find positive results and we need to confirm, then you go to SEM EDS. Otherwise, you can kind of triage that analysis and that case so that you avoid to use more expensive and time-consuming methods for confirmation. So we haven't done SEM first for that reason. But then there is another practical aspect that we haven't tested, but that's our hypothesis, and is that when you use SEM EDS, you have to place the sample under high vacuum. And we may have the risk of losing our volatile compounds when we put the sample on the SEM. This is our hypothesis. We haven't tested, but it will make sense that if we put the sample on the SEM, you run the risk of losing your organic components. So you want to do that only at the last resource if you want to confirm the results for any reason in a particular case.
So that's interesting to hear you say that you would still use SEM as a confirmation. Do you think that the LIBS electrochemical approach are robust enough to act as a confirmation themselves eventually? Or do you think that SEM will always be a part of the picture?
So I think that has to be evaluated in a case-to-case basis. What we kind of envision is to have electrochemistry and LIBS as confirmatory as SEM EDS in many cases, right? So we have been doing population studies, and so far we have been able to get accuracies ranging from over 95% when we combine the inorganic and the organic gunshot residue. So far there is good evidence that they can be as confirmatory because you are not only detecting organic but also organic gunshot residues. And although we are not being able to look at the morphology of the particle like in SEM, we developed the LIBS methods in such a way that we also gain certain level of spatial information. So even though we cannot see the particle or guarantee that we're obtaining a signal from a single particle, we reduce the sampling area to only 100 micron. And we can know exactly from what area in the stop we obtain the simultaneous detection of the inorganic gunshot residues.
Yeah, can you talk a little bit more about what steps you've taken to validate these methodologies?
So there are different steps of the validation. The first one has to do with the analytical validation of the method. So we look at figures of merit like limits of detection, selectivity, are there any other species that produce an interference with the elements that we are detecting or the organic species that we are detecting. We look at the qualitative and quantitative aspects, including limits of detection, limit of quantitation, linearity of the method, precision of the measurements as well. And then once we look at those figures of merit and we have an idea of the ground of how much we can detect and what level of selectivity and sensitivity we can detect the species, then we move to what we call a validation using population studies. So what we do is that we do analysis on real samples of shooters and non-shooters. And from those ones we know the ground truth, right? So we collect samples from the hands of the shooters and we are expecting on those samples to be able to detect the GSR. And then we have background population of non-shooters and we expect to not find interferences or something that will mimic the composition of a GSR. So we do the analysis of large populations. We are proposing around 1,000 samples in our study, in which we can evaluate how many times from a sample that has been collected from a shooter, we get a positive result. So that we can calculate the true positive rate. And those times that we didn't get a positive result from a sample that we knew that came from a shooter, then we can calculate what is our false negative rate. How many times we don't get those GSR profiles when we know that the person has fired a gun. And likewise, from the background population, we can estimate how many times we correctly do not identify any GSR and how many instances we have false positive. So in all these cases, we want to evaluate low rates of false positives, low rates of false negatives. And with those two together, we can calculate the overall accuracy of the methods. So that's a way in which we validate how many times we can correctly associate the presence of GSR with a firing event. And how common is to find the inorganic and the organic residues in the regular population.
So how is the combination of libs and electrochemistry doing? How is it fare in your validation studies?
They have been demonstrated to be very powerful and complementary. So just to give you an idea, there are elements that are detected in lips that are very good emitters, very sensitive, like barium, for example, and lead. And some elements that are not as good in electrochemistry. For example, barium is great for lips, but we cannot see it in electrochemistry because it has a very high potential of oxidation. So we cannot see it, but it's our best emitter in lips. Then electrochemistry is very sensitive for lead and for antimony too, so they complement each other. Lips has the capability of detecting almost every element in the periodic table, so it's not only limited to the standard ammunition, so we can detect many other elements that are present in lead-free or non-toxic ammunition. And electrochemistry, in addition to that, can look at the organic constituents, so we can see 2,4-DNT, DPA, ethyl centralite, those compounds that are important markers on GSR. So when we combine those two together, we get a lot more confidence in the result because the chances of getting both the inorganic and organic markers in a sample that didn't originate from GSR are going to be less likely if we evaluate only inorganic and organic GSR separately. And something that we have also seen that help a lot with the accuracy is that so far in what we have observed, it's less common to find organic gunshot residues on the hands of the regular population. So you also decrease, when you combine the organic and the inorganic, decrease the chances of obtaining false positives as well. So it helps in both directions. When we combine both techniques, it reduces the false negatives and also the false positives. So when they are together, we have very good accuracies.
Do you think the science will ever advance to the point of being able to reliably tell you who fired the gun, to distinguish the shooter from the non-shooter that maybe shook the hand of a shooter?
That is a difficult question, and so I think definitely the technology can help us to get a better answer, a better idea. but we always have the issues of transfer and persistence of gunshot residue, in which if you have residues in your hand, it could be because you fire a gun, or because you were at the vicinity of a firing event, or because for some explainable reason you came into contact with gunshot residues. Now, one of the things that we have discussed in the conception of this project is that if we have faster technologies, that it will take only few minutes to do analysis. Now we have the capability of not only doing hands. So imagine if you have an individual and you want to determine whether the person fired or not a gun, you can do now, because this is much faster, in more comprehensive cases in which you can sample the hands. But you can also sample areas that are less prone to transfer and persistence. You can sample the nostrils, you can sample the ears, you can sample the hair, you can sample the clothing. And that is doable because of the very fast time that takes to process the evidence. So now you have a better understanding of whether that person could have fired the gun or been in the vicinity, rather than having secondary or tertiary transfer that might be more limited to the hands or the clothing or a particular way of transfer. So if you have a more comprehensive case management and interpretation, I think that can help in the overall assessment of the interpretation of gunshot residue, which is complex, but I think has a lot of value in the criminal justice system. So if we can improve the ways that we can do probabilistic models on how we can use that, and use fast technology to be able to do more comprehensive studies, I think that we can eventually increase the confidence of our conclusions.
Have you learned anything that really surprised you or was very unexpected?
So we always learn different things during our research, have to overcome different challenges as well. But I think one of the most surprising aspects that we have found in the research is one of my students is creating gunshot residue standards. So she is creating microscopic particles that contain the formulation of standard and non-toxic ammunitions. So we are capturing those, we are characterizing them by different analytical methods to learn more about their composition, so that eventually we can use these standards for quality control in the forensic laboratories, and also to do more systematic studies of transfer and persistence, because eventually we will know this standard that we create in the laboratory has the number of particles per volume and this particular composition. So in doing that, we had to characterize several standard and non-toxic ammunition. So what we found surprising is that a lot of standard ammunition didn't have the standard markers when we did the characterization, and a lot of lead-free ammunition, or at least labeled as lead-free ammunition, still has lead and many of the heavy metals. So it is a challenge for us as forensic examiners because the composition is very changing and the formulations, but also the labeling of the chemical composition of those ammunition sometimes is not representative of what the composition comes from. So that has been a little bit surprising for us. We have started with 10 non-toxic ammunition, and I think half of them had heavy metals on it. So we had to go back and try to get more to really get a true representation of what a non-toxic ammunition is. So just to give you an idea of some challenges that we have experienced.
All right, I think we're just about out of time for our conversation, but before we end, were there any other final thoughts that you wanted to share with our listeners?
So I think the take-home message I would like to share with the audience is that, as with any other science, we will always be exposed to new challenges and changes in our discipline, so we have to adapt to those challenges and make use of the resources to modernize and improve our approaches.
All right, well, Dr. Trejos, thank you again for sitting down with Just Science to discuss your grant today. It was a pleasure talking with you.
It's been a pleasure. We have been honored to be able to share that with you.
And I'd also like to thank you, our listeners, for tuning in today. And for more information on today's topic and resources in the field of forensic science, visit forensiccoe.org. There you'll find additional webinars, guidance documents, reports, and conference information. And also please follow the FTCOE on Facebook, Twitter, LinkedIn, or sign up for our newsletter for release dates on upcoming resources. I'm Megan Grabenauer, and this has been another episode of Just Science.
In the next episode, Just Science interviews Dr. Travis Rush, a postdoctoral research associate at Texas A&M University, about extreme temperature fluctuations and their effect on blowfly development. Opinions or points of views expressed in this podcast represent a consensus of the authors and do not necessarily represent the official position or policies of its funding.